ready.
We're live.
Okay. Caught in the headlight. Welcome everyone. Training has just finished. We couldn't go on the stream last time because it was still working. No, I wasn't. I'm just making bad jokes here. Hello.
Yeah, so you want to recap what happened a week ago from today?
A week ago.
Yeah. And
we did more planet dataset stuff. We cleaned up a little bit. We maybe learned some new things, probably. I don't remember. We did some of that. We did some of that. Yeah, we started, right. Okay, we started working.
Yeah, we reviewed everything that we did from before the holidays. And
we worked with the other data set.
We worked with the full data set with the help of Jonah Vision as well.
Yeah, we got those data. Where is it? Planet. We got the stuff unzipped. We got our test JPEGs actually now. So that's a big folder with lots of images. Same for train.
Yep.
Does it still have the double? Yeah, it does.
Yeah. Yeah. And then and then we actually trained the model with the full data set. And towards the end, I think we
did the whole setup and started training.
So we started it probably 20 minutes before. I think we let it train for like 20 minutes. Like we started it, we were talking a little bit more. 20 minutes later, we decided to end the stream, and we didn't know how long Colab. We had a few resources up. Some said I think 90 minutes. The other one said like 12 hours of inactivity or something like that. That you'll let Colab.
How long Colab's gonna keep running
right
when
before
you're
it times
actively
out.
doing something in there?
Yeah, but it turns out we didn't need that because we thought every epoch was going to be 40 something minutes. It turns out only one was 42 minutes, and then everything else trained very, very quickly.
So I let it run after the stream ended. I went to have some dinner, I believe, and then came back to look at it, and everything was done. And so the first one took 42 minutes, and our guess right now is because that's the ResNet 50. So just because we chose such a big model for that the first epoch, when it does the retrain through the whole model, that's what took so long, I guess, right? But
that's
then
what
the rest unfreeze.
All the other ones, even in all the unfrozen, right? Well,
the unfrozen ones.
Even the first three or the last three frozen ones and the unfrozen ones all took around the same time, which I think is interesting.
But wait, so freeze epochs 4, so the first ones are the frozen ones. The first ones are the ones with the model actually, like with the ResNet frozen, and then these ones are where it goes through the whole model. So is that right? Because I believe that's what I remember, and also it fits with what we're saying here, freeze epochs 4.
Yeah, so the first 4 frozen epochs, right, are it's like building on top of ResNet 50.
ResNet 50,
right.
Yeah.
And then it takes that whole thing and then trains it for 3 more.
Yeah, then it
and I think that's the first
3 from.
That's the first 3 number in that function call, I believe. If you scroll,
Yes. But so that's interesting. So when after the ResNet 50 was unfrozen, we had 1 minute each, and the first epoch of ResNet 50 frozen and just training with the parameters and everything as they come with ResNet, but then add on our couple of layers at the end. That's what took so long.
Yeah.
If anyone knows why.
Yeah. What's interesting is like, it really, I don't know, I'm finding this, like, the accuracy always to be really interesting, and like in the relation on how much time is spent to train. So like the first one, 42 minutes, fine, because we chose ResNet 50, and it's a big data set too, right? 86.86 accuracy. It's not bad, right? And then goes up almost 10 points, and then from here it just like gets closer and closer and closer. But it also seems like, I don't know, I think most people would be happy with not even doing the fine tune, afterwards, right? Like this, after the frozen epoch, for this
still is
0.95.
pretty significant increase though. If you like, it's like, I mean, yeah, it's 1 point.
Yeah.
94.5 to 95.9, 1.5.
Mm-hmm. Yeah, it's interesting. Like, I wonder, and we can maybe not do this, on this stream, because we're also talking about moving forward with the course, but to have like, maybe just like spend time and like research and see like, okay, running all of the images through these different scenarios of like, okay, we're just going to use the frozen epochs. We're not going to fine tune after they're frozen. So we do have this like 0.95 accuracy, and then see, I would like to see like how good or where is it messing up in relation to like the fully fine tuned one. And is it, what is it actually fine tuning? I don't know. Anyway, who knows? AI, man. It's taking over. No, but this was cool. This was a nice surprise that, it actually worked and it didn't time out.
Yeah, wait, I kind of like was expecting it to just time out because I assumed I wouldn't have the patience to come check back every hour for the whole night or whatever. So I'm happy that this just worked out. And I exported the model. So we got our full learner, hopefully still sitting around here. There it is. So now we're ready to import this, and I'm going to do that right away, Henrik. While you talk. I'm not even gonna, I just ran this first cell, but I'm not even gonna do anything else here.
Sorry, what was that? You want me to talk? You want me to tell a story? No. Oh, no.
Do
okay.
Not.
I will just keep quiet.
Okay, we gotta get, no, don't run this. So plan for today, right before I start dabbling around here messily. Plan for today is that we're just gonna import this trained model, the full learner, like sort of planet data set trained on all of the JPEG images that we did last time. Import the model, the learner, and do a couple of, what's it called? A couple of predictions. See how it goes. Maybe compare to the ones that we still have sitting further down in this document, and just see whether it does better job on the same images. And then we said we're going to move on with the course, because we haven't looked at any of the fast.ai materials for quite a while, and we've just been off on our own tangent going in this planet data set.
Yeah, I think it's time to get back on the course and
feels like
keep it moving. Yeah, for sure.
We're still like not even halfway through, so I think 2021. Let's get going, right?
Yeah, hopefully we finish this before the end of the year. That would be nice.
Full learner, is that what I called it? Yep. And then we need a path. It's gonna be anyway, it says I think it tests the current working directory. What is it? Nick, I just recently remembered that I don't have to do this weird syntax with the slashes, but that I can do something, an actual method on it, which feels a little cleaner. But now I obviously don't remember it. It's not iterders. But how would you say if you want to combine like two paths together? What's a word for that in English?
Like concatenate it?
Yeah. But that's not it.
I know.
Path live, join path. That's it. Just gotta start Googling. Don't even need to Google it. Path.
Jonah Vision coming in with join.
Join. It's join path.
There we go.
But join, thanks. That's the right direction. Yeah. Okay, join path, and then we are again content G drive, my drive, data. So happy that I made such a deep folder structure here so that every time I can just keep typing. All right, there we are. And now we should be able to load the learner with this path. Should it be consistent? Sure. Let's practice the new method. All right. You don't like it, huh? Load learner, path to chain path. Can't get attribute getX a module main. All right, seems like the first thing worked. Let's try this again. Are you fine with this? Yes. So chain path is okay. And then am I messing up any brackets here? Second eyes. That looks fine. Full learner. Okay, let's try. That should make a difference. And it doesn't. Can't get attribute getX. Wait, why is the learner still using this getX functions that we defined further down? Shouldn't this just be the full, like everything just exported? Am I being dumb? Like it's telling us that it doesn't understand this one because I didn't run this cell before.
So if you run that now, you're
but why would it need that? I don't know. I mean, that's just the error message I'm getting here.
Yeah.
But I'm just confused. Why would it need that? I'm just getting the exported program, essentially, from my understanding. You're happy now, huh? That's confusing. Let's see whether it works. Okay, so we got that path.
So when you export it in that pickle file, it doesn't, I guess it doesn't also include those methods that we're defining elsewhere, right?
Why is it using them? Like where is it using them? Is what I'm wondering about. Okay, I'm gonna get some file name here.
Is it not using it like further down to collect? Because we are using getX and getY further down, right?
Yeah. Yes. But we're using that for training, like so that it gets the X, so that it knows where to get the training data from, but not for predicting.
Man.
It's fine though. Look at that. So that's interesting. I'm gonna take a note because I don't understand it.
Okay.
Oh wait, Generation says something. I think the learner needs to know how to process the data. How to process by yes, but isn't that, I mean, it just get X is just to get the get the data, the image data for the model to run, is my understanding of it. But
right, for training.
Yeah.
I don't know.
I don't know either. Why?
That's it, period. Why?
Why is loading trained learner with, what is it? With load data, load learner. Require get X be defined. Like, so there was this early couple of times back where we're making this we're struggling with making this little program that we could then upload and predict stuff, right? The dogs. And there we also had an exported learner where we would go and import the learner to, but it's just a self-study, like it didn't have any connection to the
right
data otherwise, which is kind of what I would expect.
Yeah, maybe because we're not, for the dog stuff, there wasn't, did we have like a getX and getY function or methods on that?
No, I think it was using some built-in ones. Yeah. Okay. So maybe the built-in ones come automatically when you do load learner.
Mm-hmm.
Interesting.
But
so yeah,
maybe there's a way to like also package those functions into I don't know. Yeah, I think that may be it, right? Like the built-in ones, when you export it as a pickle, are obviously included, but
Yeah,
maybe there's a way to
imports.
yeah.
Maybe they're not included, but when we import fast.ai vision all or whatever, it gets all the default things to get the
yeah, we didn't run the right exactly.
Okay, interesting.
Yeah, it just seems like it was another dependency that we have to do beforehand. So yeah, sorry, I'm eating breakfast while you're doing this, even though it's almost noon here.
getX is the category block in the data block. getY is the category, from my understanding. getX is the data, right? getX gets the path to the image, so it's the actual like getting finding the image, and getY is getting the multi-category tags.
Yeah, but either way, like I think that's kind of, if we define any sort of function or method, right? Like that has that.
I was just responding to John Visions.
No, I know. That's what I'm saying. I think like it doesn't really matter because if it's what it's using it for, like it's predicting or whatever, there's just the dependency on it. That's why I think it was having the issue. So
yeah, interesting though that it still has the structure of what I assumed is just drawing data for the learner, for like doing the models, building the model. That is still that. Okay, so we did some prediction number 1, test 42.
Right, yeah.
Clear primary. What do we get? This is this one.
That looks about right.
And now, what's a nice way to compare these? We got here clear primary 0.99, clear, and 0.9295. And here we have all sorts of numbers. Oh no, not that again. Okay, so E.
Well, we have, there was one that was 9.
Do you see the lowest one? This one?
No.
9.93.
Nope. Keep going. There.
And this too.
That one, yeah.
Yeah. So this two, 9.9920 and 9.9392. And I already forgot what these ones were. I gotta copy this, huh?
One was 9.2 or 0.929.
So wait, I got it now. On the, what was that, like the sample data set? We got and that was also clear primary. And the numbers compare as follows. We have 9.93 and this one was 9.99. So the first one was more secure in the when we didn't use the full data set. Or it's a different order. That could be that it's a different order now, the labels, because that looks pretty similar.
Yeah.
Okay, let's see the. Maybe that's what it needs all of that stuff for, right? Like it still needs to tell us, right? Like it still needs to know where the category, what the categories are. But that would be get Y. I'm making half sentences today because why not? Fun stuff, because Nick is eating breakfast. So why can't I just do half sentences? Huh? Any objections?
Nope.
Right? Okay, do you remember how we get the list of all of the learn dot categories?
No.
You don't, huh?
I don't remember.
Oh, Nick. Just eating your breakfast, oblivious to the world.
Well, I paused now because, you know, this is more pressing than my breakfast.
Because I've kept harassing you.
Yeah.
That's the training. I guess I cut it out of this one.
I was gonna say, I think we took it out of this one.
We gotta find a quicker way to. Yeah. But we gotta have a quicker way of finding these things than just always going back to some past vocab. Nice. We have a quicker way of finding these things. We have shown a vision.
Oh, vocab. Yeah, that's true.
Learn dot. It's not on the learner. I guess it's on the data loader class, which we don't have in here. But there must still be a way to get it through the learner. Okay, how to get labels.
Oh, it sounds like Martin's back to full sentences, so I'm going to go back to eating breakfast.
Fast AI. You really don't like how I Google stuff, huh? Learner. Do you have some sort of vision data? Okay, vocab. Can I type it? Not in there. Label. Function. Under data. That's all. Interesting. Okay, what's my fastest way of getting to this? I could just remake the data loader here. And then I think I can call it on that. I don't really want to do that, but we need to know. Like, we need to know whether what you're eating is healthy or whether it's increasing your cholesterol levels. We need to know. Your silence will not prevent you from dying from heart disease.
It's a bagel.
Say a good thing?
With some sort of cheese, avocado, tomato, red onions, pesto, and hummus.
Okay.
Yeah, it's very it's good. I don't think it's increasing my cholesterol though. Sorry to disappoint.
No,
Mister.
Good. Disappoint? No, that makes me happy.
Oh, good.
I don't want you to die.
What if my cholesterol's too low?
About me. Oh, Nick, it's complaining again.
All right, what do we
Does that shoot your cholesterol up in the air when you see this kind of stuff happening? Is it going all like crazy?
This is worse than the bagel I'm eating, for sure.
This is the same problem. I have to run everything again. It's complaining because there's images that are not in there. But I don't wanna. I'm so whiny today. Okay, yes. do this?
I was gonna say, don't we have this in like a different collab or different notebook?
No, the Jonavision already told us that it's vocab, but the problem is vocab only goes on the data loader. Was when you were taking the 5th bite of your bagel and you were all indulged in hummus sweetness in your mind. So you probably missed what was going on here in the important aspects of life.
You're absolutely right. And I appreciate you keeping track of my bites and when things are happening. It helps me realize when I'm drifting off, and I apologize to everybody.
That's good. Don't accept his apology. He's just going to do it again.
I'm going to do it again.
See? I knew it. Okay. Yes, I know you're working. Collab. Okay. So I got our data loader back. I think. Maybe. So now we should be able to do vocab on it. DLS r.vocab. Bam. Whew. Okay. But is that the same one as the one? Yeah, it should be.
I think they're in alphabetical order. I think that's what we discovered.
God. Yes. Okay. That means
bam bam.
If they're anyways in alphabetical order. But that then means that the accuracy has actually changed significantly. That this one went from 0.9919 for classifying clear to 0.9939. It didn't change that much.
So yeah, and then I think the other one changed. One of the other ones changed more. It was like 9.2 went to 9.9. Okay, so
this went up a bit. This went from 1.9 to 3.9. Okay, and this one 9.99 in the new one.
Right there, 9.2. So that also went up. That went up kind of.
That went by like 6 points nearly. Yeah. More. Okay.
So
that's good.
It was worth it.
All my complaining was unnecessary. But yeah, it was worth it.
But I think it's also
for this one first test.
So, yeah.
Okay, wait.
Do you want to look at the other accuracies as well?
Yeah, let's try a couple more images. I'm just gonna.
No. I was saying like from the beginning. So like just scroll to the front of both.
Okay.
So
front of what?
No. Scroll a little bit down.
Scrolling fingers are coming. There they are. Scrolling.
There, a little bit more.
A little more.
Okay, right there. And then go on the sample data set, go all the way to the front to see the first item in the array.
Okay, I need my other scrolling fingers for that.
So yeah, this way.
That's it. The other way. You want to go that way?
Yeah, to the front.
I can do that.
So what happened here too is like, let's take this E, -3. So like 1, 2, 3. Yeah, moving the, right? Because we have to move the decimal over 3 points.
You know what I'm going to do, Nick? I'm going to give you annotation capacities. And then you can draw on my screen. So does that sound like fun?
Ooh.
I think you can just do that anyways. Or do you want me to draw?
Annotate. But can you see if I
believe so. Give it a go.
Can you see it?
Yes.
That's
you made
so
a blue
cool.
little thingy.
Oh, wow. This just changed the game. Where are my glasses?
You want to see the blue little dot that you made? It's beautiful.
I see it. No, all right. So this, all right, I'm going to, and I have an eraser and everything. I remove the dot. This is.
Generation saying, if you want to have a good time, try to predict to CSV using the test set on the 40K images.
Did we?
You mean the 40K test images that we have in there? Yeah.
Wait, so I'm also looking at these over here. So like this one, for example.
Wait, I don't know. I don't see what you. Yeah, now I see. Okay. Chill, Martin.
compares to this one, right? Like these two should be the same, but that number is like significantly different, isn't it? Like this e minus 5 would put this like 1, 2, 3, 4, 5. No?
Well,
or is
it
that
goes into the other number?
Isn't
it's
that
actually part of the other number? You could just do you have like remote control, or can you just draw right now?
I did draw.
Right, but can you also do something else on the screen?
Oh my goodness. Wait, yeah, hold on.
No, you don't have to. I'm just asking.
Okay, so it doesn't, and tell me if this is, maybe I'm not understanding this correctly, right? Like e minus 0.5. Doesn't this equal 1, 2, 3, 4? This?
Generation's making fun of us about scientific notation.
I'm like obviously not like doing this correct, because it should be like,
why
why
are you
is
doing anything? No one sees what you're doing.
You don't see my typing?
Oh,
there you
it
go.
just takes really long to come.
Oh,
Or maybe you have to, yeah.
Oh, and I can't.
Maybe you have to like.
And I can't edit it.
Well, what about? I can't do. Oh my god. I think if you just print it out, it's gonna convert it into
I'm done with this.
Non-scientific number.
This was cool.
Dumbos like us.
You guys in scientific notation. Yeah, we get it. Can you just copy this? Hold on. All right.
Doesn't that work if you just go in here and you print it out or something? Doesn't Python convert it for me?
I'm going to finish my bagel and increase my cholesterol.
Don't do it. Oh, no, it doesn't. So print float. Just messing around here. This is a float, huh? Well, I can't. If I put it to an integer, it's gonna be like 0. Of course. Yeah, that's not the way to go. I'm sure there's like some sort of. I could probably do it. Oh my god, this is so messy. I could probably do an F string and give it like some how many .2 I want to see. No, that doesn't work. Yeah, it's not a string, of course.
I think it's just minus those numbers. So like it's just moving the decimal place over. So hold on, I don't want to stop remote control. I'm just gonna annotate again.
Yeah. I guess you can't.
325.
You can't even pretend to learn about data science if you don't understand scientific notation, huh?
Isn't this the same? Doesn't that equal that?
So 5 places over. 1, 2, 3.
No, it's the other way.
1,
it's minus.
2, 3,
so you're moving
4,
it.
5.
You're moving it the other direction.
Right. You're adding them this way. Okay.
Oh wait, hold on. This is also
1, 2, 3, 4. But that's
3.25.
1, 2,
E
3.
minus, hold on.
So that would be 4. What you did, right? E to the power of minus 4.
Yeah, but I just I did. I didn't write the first number correctly. It should have been 3.25.
Yeah, do it, Generation. Generation's jumping on and it's going to teach us.
Do you have the stream link? Did you send him the stream link?
Yeah, I did. Yeah.
Nice.
Do it. You can get remote control and mess up the whole. Clarify everything. Well, in case you want, you're free to join on and teach us scientific notation. But otherwise, that sounds good.
No.
And
it's just going to float in the middle of the screen.
That's really... Well, but Nick, that would mean that the second one would have changed like really, really significantly if that was the correct thing.
That's
from
what
0.2
That's what I'm saying.
0.0000.
That's what I'm saying. It's like 0.0003.
I see.
Versus like, so the sample, that's what I'm saying. Like the accuracies for the positive stuff is like great, but then look at the negative ones too. Is like, and this -5 is interesting, but like you have -3s and -4s, and you're not seeing you know, the
right,
one,
they're all very, very negative compared to here, where they're all like pretty relatively similar.
Like the first one is kind of
saying,
the first one is kind of similar, right? Except it's that would be like 5. That one's -3. It would be -2 in the sample data set, like 5.41 -2.
Mm-hmm. So wait, John Ovation, can you confirm this? Are we understanding this correctly? This here, 5.57 blah 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 e to the power of -3 is
no. I'm saying it's
0.05. No, you're saying it's not. So
yeah,
it has
let me type it
0.
out. So 5.57 e minus 3 is the first one, and that would be 0.00573. 1, 2, 3. Correct. That I think is correct. And then to change the other one in scientific notation, it would be 5.41
times
e minus 2 would be
0.0541.
0.0541.
Okay, I see. Makes sense. So it actually did change also significantly for that when it changed the whole order of like
there's
one whole decimal point.
Right? But then you look at all these other ones, and it's like 5 and 4 and 3, and it's like these are huge. So I thought that
huge differences.
Yeah, I thought that was interesting to just like a quick observation going through.
0.052. Okay. Yeah, so this training with the larger data set, if I'm trying to synthesize this somewhat, it becomes much more sure that something is not what it's not, and it becomes a little bit more sure that it is what it is. Like it's very sure it's e to the power of minus.
It is what it is.
Let's have a bagel on that.
It is what it isn't, or it's not what it's not, and it is what it is. And on that note, everybody, thank you, Martin. Yeah, no, I think I saw that really quickly as we were scrolling through. It's like, yeah, okay, fine, the 9.99, that should stay the same. But looking at the ones that it really doesn't know, the difference just became so much more drastic.
Well, not the ones that it doesn't know, the ones that it knows it isn't.
Right. I guess.
Yeah.
It knows what it's not, and it knows what it is.
It knows.
Very self-aware. Did we just create sentient AI?
Self-aware image classification. Yeah, that's. I like that. Sounds good. Sounds like a good thing. It knows what it is, and it knows what it isn't. The full data set became self-aware. Good. That's a good conclusion. Let's classify a couple more, but it's probably going to hold that trend, I assume. 999. For 999, we get this tensor. And so it's just not displaying them in scientific notation here also because the numbers are so much higher. So there's no need for them. I don't need an answer. I'm just saying this to the void. I'm just saying this to the bagel. Hey Bagel, how are you doing?
We should have titled this. We're making self-aware AI. No, seriously.
Yeah. I don't think so.
I think we did. I think it's hard to dispute that we didn't.
Okay, this is number 1, and test 9999 was the other one we wanted to do. Predict me. Good numbers. Okay, so what we got here? Another set of beautiful E numbers. Oh, you know the E numbers in food?
E numbers in food?
No,
what is that?
Oh, maybe that's a European thing. In European food labeling, there's the E numbers are usually like the stuff that's in the food that's like somewhat, I don't know, that has like a specific level that can only be in there because it's actually kind of toxic. Some of them, not all of them. I think some of them, it's just like artificial food stuff. Okay, so the second one, which is clear, that fits with, does it fit with this? No, it doesn't. Oh, this is e to the power of minus 5. 9.95 we got. And this one was 9.91. And then we got another boring clear primary. The second primary is 0.88. And here we have 9.9965. Wow. That's a significant increase. And all the E's are in -3, -4, -4, -3, -5, -4. Yeah, I guess it gets a lot better, huh? Actually. I can't hear you chewing right now. You accidentally switched off your microphone, so I'm missing out on all that good chewing action that's going on here.
It was no accident.
Oh, why?
You don't want to hear me chew.
Cool. That's I'm impressed of how much better this is now that I understand what.
Yeah.
For a little bit how the E stuff works. Okay, so let's try another one. There was 999,237. We got a nice little cloud sitting in here. 237.
Yeah, I mean, just to respond to Mellinger in the chat, it would be cool to like toggle it back and forth. I don't know, we try to print it, but we just don't know how. I'm sure there's a way to do it. I don't know, we just don't know how to do it. Or even just like, print it. I don't know. We tried to print the floats and all that stuff, but it didn't work.
Okay. Can you please chill and stop?
Interesting. So Martin,
yeah,
Jonah Vision just said you could float it and then specify the decimal places, and then maybe it'll.
Isn't that something I tried?
No, you just floated it.
No, I specified the decimal points in the.
I think that was between my chews. I don't know.
427. Is that the right one? My memory is like a little sieve. 237. 237. It didn't quite feel right. I got a 3 out of 2. 237. 273? 237. Okay, let me try that again. Can I specify the decimal value on a float directly? Or do I have to do this weird? I'm pretty sure I don't have to do this weird detour that I did with doing an F string.
Well, so I don't know. You want to look at the chat and look at there's a Mellinger put something for NumPy stuff.
Option,
and then Jonah Vision made a good point.
Set print option.
Yeah, Jonah Vision made a good point that if you did do decimals, it was like 2, but we need, like 10.
Let's try both of that. So that would be 0.10. Okay, yeah, that works. Okay, so this is one way you could display it, and then let's try the other thing. That Mellinger, numpy.set, and then it does it.
Set print options.
Set.
That's cool.
Underscore print options. There it is.
Suppress equals true.
Suppress. That's true. And that just does it for all of NumPy outputs, it seems. So when I run this again, what you're gonna do? Still uses them. Because they're not NumPy.
Maybe because it's a tensor, the fast.ai.
Right. Maybe if we'd pass the tensor to a NumPy, that might work. I don't know. We could try that. What can I make with NumPy? NumPy dot. Do they have something like, no, that's data frames. That's pandas, the series objects. NumPy dot array, probably. Yeah. Okay.
There you go.
There it is. Yeah, that works. Mm-hmm.
So weird spaces at the end of. Oh, I guess because they're just empty. They're not. Interesting that they're not just adding zeros there. It's just empty spaces.
Mm-hmm.
For the ones that are.
Maybe it makes it easier to read.
Yeah.
You know.
Mm-hmm. That's really cool. That's nice to know.
Yeah, that's nice. So both of this works. You can make this weird detour over the F string and just do more decimals, and then also this works.
Yeah, Jonah Vision was saying maybe you don't need the decimal at the 10. It could just, if you say 10 places, like not 0.10. So after that colon in the F string.
No, I don't think that works.
Period. No? Yeah.
Oh, it does.
Yeah. You're just saying 10 places.
Okay.
Cool. Oh no.
Nice.
Jonah Vision didn't say that, but it still worked.
It still worked, yeah. I think. Okay, yeah, I just know it like that with the point, but it seems.
Yeah. Well, I noticed that. Yeah, I noticed that there was no period, the decimal point, in the comment. So I was like, oh, maybe that works.
All right,
that's funny.
Surprise.
Anyway, we learned 2 things today.
Why? All right.
Oh man.
So we got partly cloudy primary. Is that the same? Wait, now I'm very confused where we are. Partly cloudy primary, and we got the numbers. So these are our new predictions, and these are our old predictions. Okay, so I'm gonna move these 2 together so we can compare. Wait, why
that looks
this? Right. 2, 3. So this one has actually has ease in there too. For some reason, because I guess it was more sure that it's just partly cloudy in primary. Where am I going? I got lost. No, it's further down.
It was for what? 237, right? The image?
I got lost in this small document. Is it further up? It's here. Okay, that's why. So this is our new one, I believe, and then let's also make an NumPy array with the old one, old 237. Okay. And let's also print it out. Old 237. And then this one is new 237. Okay. All right, so here's our comparison. 0. The old one. Okay, again, it got much more secure that something is not it. 0, pushing it a couple of decimal places. That's very impressive. I'm impressed by this increase.
It's incredible how much better it is, right? At saying that this is not, or not that this is not, but that it's really not really doesn't think it's clear primary, or the blow
4, 5, 7.
blow down or whatever.
0.26. Those are 0.26 and 0.27, and then we got 99, and is that partly cloudy in primary? I assume that the 0.99 is the so this is going to be the second one. That's going to be partly cloudy. 0.62.
I think Jonah Vision, I think maybe on the next stream I'll play my guitar in the intro and the outro, and maybe Martin can sing about fast AI or what we're gonna learn.
I can't sing. Don't do that to me.
Put Martin on the spot too.
Well, that's the wrong one. 0. Which one am I picking? Oh, I went too far, so it's number 8. That's 0.62. I just want to know what that is. In our vocab, that would be the data loader R vocab number 8. There should be partly cloudy, I guess. Cultivation. So it's 62% categorizing this as cultivation
in the sample set, with the learned on the sample set.
Right. Okay. So and then in the new one, how much does it think it's cultivation?
Wow.
Okay, very, very low. Thanks for innovation. Neither have I been paying attention to what I've been doing.
I mean,
nor
really,
has Nick.
Yeah.
I don't think anyone has. Well, you know what? Whatever.
No, come back.
Oh, I just realized that I wanted to switch off my screen, but then I switched off the camera, which doesn't make any sense.
Oh man, no. So this is actually really cool that not only with the full data set, but we're also not comparing truly apples to apples with like training, right? Because I think we trained the sample one on ResNet 18. We're training this one with the full set on ResNet 50, but it's kind of it's cool to see the huge difference in categorization with ResNet 50, ResNet 18, and then the full and the sample data set. So anyway, nice little detour we took. What do you want to do for the rest of the stream, since no one's paying attention to you?
Maybe you should decide.
Do you want to, I could tune my guitar, we could play a little bit, we could sing about data frames and data loaders.
I'm actually pretty excited about this right now, but I see that it's not really carrying across to anyone, so that's okay.
Oh man,
but this is really exciting. Like it actually changed. I like the way that it got better, because I don't think that the classifications seem to be the same. It's still saying that it's cloudy and primary forest. So if you just look at the cultivations, if you just look at the classifications, you wouldn't really see much of a difference. But if you look a little closer and understand how to look at scientific notation, then this is a significant difference. Mm-hmm. Like it's just got very sure that it's not all of these other labels. I think that's pretty cool.
I think I said that 12 minutes ago.
All right, I told you. You say what we do.
Do you want to write a song?
Of a bagel.
Do you have bagels in Austria?
No, we don't. Of course we don't.
Really?
Let's get bagels. Come on.
You don't have bagels?
I'm pretty sure we have some bagels somewhere.
I'm pretty sure you definitely have bagels in Austria.
Go to some American bakery. Is that a thing?
American bakeries? I think we call them like Dunkin' Donuts over here.
Yeah, I don't think we have those.
That's your American bakery. No, we have.
All right.
We have. Anyway, yeah. Continuing on.
Did I get your attention, Nick?
You're getting something.
Okay.
All right. So where are
response.
we? Where are we?
We are
in all of
ridiculously, but I guess appropriately for our actual knowledge, we're here.
No.
Yes.
Are we?
Yes, this was all multi-category. We looked at chapter 6 multi-category, and then we went off on our planet tangent for the past month or so and looked into some multi-category classification with that data set. So here we are, chapter 7, Resizing and TTA.
Okay, so we're an hour in. How do you feel about jumping into the new chapter?
Good.
Yeah?
Good. I feel great.
You feel great?
Yeah, perfect.
Really good.
I feel motivated.
Let's do it.
I feel like I already clicked it. That's how I feel about it. I feel like I'm gonna close the Raspberry Pi article that I had open at the beginning because I was like, oh, let's just do something completely different today. It's
so
gone.
How many?
Did you see me close it?
How many more chapters do we have? Another 7?
I just closed it. Yeah, I think so. Fast.ai. This one. We have another. It's a book, you know. It's the first book I'm reading in my whole life.
No, it's not.
We got 20 chapters, and we are starting at chapter 7, so we're about a third through the course.
Remember when we said this was going to take us like maybe 3 months?
I think
we started in September.
I have the feeling that I probably said it's going to take us a year. Or maybe I didn't say that. Maybe I was just thinking it. We do this, theoretically, we do it twice a week. So the honest truth, which probably anyone who's ever watched the stream that you know already, is that we spend basically no time on learning this apart from when we're on the stream, because that's what we set out to do in the stream, to actually like learn this or a little bit about this topic while we're streaming. So we usually do two days a week, on Mondays and on Thursdays.
Yep.
Is that right? Correct. And we do like 2 hours, sometimes 2.5, sometimes 3, but usually around 2 hours.
Yeah.
So it's, I guess, 4 hours a week.
Yeah, 4 hours a week. And initially we started doing, it was mostly just learning. So we were going through the videos, which was kind of boring a bit for people watching, because, you know,
and also kind of for me, because
for us, I think it was just I was playing the video. It was a
subtitles
audio disaster. So we decided to go to reading the chapters in the book, and then at some point we said, well, let's just do Mondays we were going to learn, and then Thursdays we were going to build something. And we followed that format for a bit until the things that we were building or we were working on, we made probably a lot of stupid mistakes, and that build carried on to the following Monday and the following Thursday a couple of times. And then we did some like silly stuff over the holidays, like a turkey classifier, and
that was a disaster. But also, we just started. I mean, I guess that's the way that it seems we both learn, more or less, is just trying out stuff and playing around with it more than going over resources, probably, which has proven to be sometimes very often like the things that we get confused about, and we just read a little on and then it's explained in the materials.
Yeah,
this has happened a lot, but I don't know, it's all about having fun while learning something for me, and like going into a topic that I've been wanting to learn more about for quite a while. So
yeah,
but yeah, Mondays, Thursdays, 4 hours
for the most part,
pretty much.
Yeah, cool.
All right, so we're at chapter 7, Resizing and TTA. You have any guess what TTA is going to be, Nick? before we scroll and find out? Oh. No, I don't think that's it. I thought for a moment that's already explained.
TTA. I have no idea.
Yep.
Total time something.
Total time art.
Ah, there you go. Or training. Total training.
Maybe training the art model. Yeah, you go ahead. I've been talking all the time today.
All right.
Do you want to go read?
Sure.
Total time algorithm. Bam. Generation's been. How did you probably did already the whole book.
Yeah, how far are you, Jonah Vision? And also, I'm wondering, Mellinger, are you also in the course? Are you taking the fast.ai course as well? And then in the meantime, I guess Martin can answer that. In the meantime,
I can answer.
Yeah, because you can look at the chat.
Sure.
All right, so training a state-of-the-art model. This chapter introduces more advanced techniques for training and image classification models and getting state-of-the-art results. You can skip it if you want to learn more about other applications of deep learning and come back to it later. Okay.
No, we're not going to skip it, Nick.
No,
don't even think about it.
Knowledge of this material will not be assumed in later chapters. Are you sure? This is a pretty convincing first paragraph. Okay. All right, so Jonah Vision's not at the same place, and then Mellinger hasn't started yet, but thinking about doing it. Okay, cool.
Uh-huh. Yeah, cool. It's a really good course. Like I think it's very well made.
Mm-hmm. Yeah.
Very well made.
You sure you don't want to skip this one?
So you would just want to skip chapter 7
look,
and move on to
knowledge
chapter
of
8.
this material is not assumed in later chapters, so it's not saying that this is going to help us in later chapters. And if we want to come back to it, we can. All right, let's look into it and then decide if we want to skip it after we've learned it already.
All right.
Okay.
How long do you think it is? I think it's everything expanded. It's not that long. Look at that.
This is like a split two sections.
I think that's a nice 1 hour us reading over this, maybe
reading over it.
Stuff.
Yeah. Okay. Fine. We will look at what normalization is, a powerful data augmentation technique called mix-up, the progressive resizing approach, and test time augmentation. To show all this, we are going to train a model from scratch, not using transfer learning, or using a subset of ImageNet called ImageNet.
I think that's funny, huh?
Yeah, I do. It contains a subset of 10 very different categories from the original ImageNet dataset, making for quicker training when we want to experiment. Okay. It's going to be much harder.
Saying that he skipped that. The course guy also skipped that content during the videos, but he must have skipped a lot of stuff if there's 20 chapters and there's like 8 videos or 9 or something like that. Also.
Okay. This is going to be much harder to do well than with our previous data set because we're using full size, full color images, which are photos of objects of different sizes and different orientations in different lighting and so forth. So in this chapter, we're going to introduce some important techniques for getting the most out of your data set, especially when you're training from scratch or using transfer learning to train a model on a very different kind of data set than the pre-trained model used.
Okay. ImageNet. When fast.ai first started, there were three main datasets that people used for building and testing computer vision models. ImageNet, which is 1.3 million images of various sizes around 500 pixels across in 1,000 categories, which took a few days to train. MNIST for 50,000 28 times 28 pixel grayscale handwritten digits. CFAR 10, 60,000 32 times 32 pixel color images in 10 classes. The problem was that the smaller datasets didn't actually generalize effectively to the large ImageNet dataset. The approaches that worked well on ImageNet generally had to be developed and trained on ImageNet. This led to many people believing that only researchers with access to giant computing resources could effectively contribute to developing image classification algorithms. We thought that seemed very unlikely to be true. We had never actually seen a study that showed that ImageNet happened to be exactly the right size and that other datasets could not be developed which would provide useful insights. So we thought we could try to create a new dataset that researchers could test their algorithms on quickly and cheaply, but which would also provide insights likely to work on the full ImageNet dataset. About 3 hours later, we had created ImageNet. We selected 10 classes from the full ImageNet that looked very different from one another. As we had hoped, we were able to quickly and cheaply create a classifier capable of recognizing these classes. We then tried out a few algorithmic tweaks to see how they impacted ImageNet. We found that some that worked pretty well and tested them on ImageNet as well, and we were very pleased to find that our tweaks worked well on ImageNet too. Wow, success story right here. There's an important message here that the dataset you get given is not necessarily the dataset you want. It's particularly unlikely to be the dataset that you want to do your development and prototyping in. You should aim to have an iteration speed of no more than a couple of minutes. That is, when you come up with a new idea you want to try out, you should be able to train a model and see how it goes within a couple of minutes. If it's taking longer to do an experiment, think about how you could cut down your dataset or simplify your model to improve your experimentation speed. The more experiments you can do, the better. See? Let's get started with this dataset. ImageNet. Okay, first we'll get our dataset into a data loaders object using the pre-sizing trick introduced somewhere. Blocks, we're using image block category blocks. It's going to be single categorization. Single category, not multi. Image files, get Y, parent label, item transform, we do a resize on them, and the batch transform, augmentation transforms to, what are those again? Augmentation transforms is those are the stretching stuff.
Stretching, twisting.
Yeah. Okay. Sure, let's get undo make a batch size of 64. So get our data loader, and then we do a training run that will serve as a baseline. XResNet 50. I wonder what XResNet 50 is. Using cross entropy loss flat. Training on accuracy. Learn fit one cycle. Okay, that's a good baseline. Okay, we don't know the baseline yet, but it's going to be a good baseline since we're not using a pre-trained model, but we can do better. When working with models that are being trained from scratch or fine-tuned to a very different data set than the one used for the pre-training, there are some additional techniques that are really important. In the rest of the chapter, we'll consider some of the key approaches you'll want to be familiar with. The first one is normalizing your data. Do you want to wait for this? No. No time to wait. Keep going.
Hold on one second.
Eating a bagel?
No, I was finding this Google
useful stuff.
I'm doing somewhat useful stuff. Yeah, that's what we're looking at right now. This Jupyter notebook, if anyone wants to follow along at their own pace. All right, normalization. I'm handing off the useful stuff to you. Also, wasn't listening to anything you said previously, so you're gonna have to.
Well,
it's fine.
So we're training. We did some data loaders, and what it was essentially saying is they used. Okay, so there's a success story in here how they developed a data set that that did some nice that you could quickly train on to get results that would be comparable to if you would train it on ImageNet. They built this data set.
Okay.
And the message is like you want to have a data set where you can, like a small one, that where your results are kind of like applicable also to the big one that you actually want to train on. And you just want to have a fast iteration speed.
Okay.
I think that's my main takeaway, and that you can find some data, like you can build data sets like that.
Cool.
And then we're doing some training to get a baseline model.
Nice. Oh, it looks like how long is the training gonna take? What does it say on there? 2 hours, 31 minutes.
Oh God. Wait a second. That sounds suspicious.
Aha. Good job.
That does sound suspicious. Okay, so we want to have a wait. Change runtime type. Get ourselves a GPU.
Yep. Thank you, Jonah Vision.
It's I haven't figured out when it, because often it just automatically gives us a GPU and then sometimes it doesn't.
Mm-hmm. You want to go back to, yeah. Do.
What?
Maybe it gives us the GPU when we've opened that same notebook. Because this is a new chapter and we haven't done that
you're right.
in a while.
That makes sense. So when you want select a GPU, then it just sticks with it.
Yeah. Maybe.
Maybe. All the mysteries of Google Colab. I think we're good now. Oh, why? No, yeah, that's fine. We don't need you anymore. Anyways.
Yeah. Fun.
What you doing?
Just hanging.
What's it doing? It's just hanging. Yeah, okay. Chill.
Colab's just yelling at you. It's like, dude, I'm working.
It's running! Stop clicking!
I'm doing my best, man.
I gotta stop scrolling around. I'm constantly scrolling around.
All right, it's done. It's done.
Finger ties.
Scroll.
Like the ones that you have.
Scroll.
Scroll like your life depends on it. Okay. Did you do all of it already? Data block? I'm gonna do it again. Okay. Now it's gonna be done right away, I guess.
Yeah, probably like 2 minutes.
Okay.
Cool. All right, so where were we? That's a good baseline. Normalization. When training a model, it helps if your input data is normalized, that is, has a mean of 0 and a standard deviation of 1, but most images and computer vision libraries use values between 0 and 255 for pixels, or between 0 and 1. In either case, your data is not going to have a mean of 0 and a standard deviation of 1. Let's grab a batch of our data and look at those values by averaging over all axes except for the channel axis, which is axis 1.
It's a channel axis.
Yeah.
Do we know what that is?
Mm-mm.
Channel axis of an image. This is probably one of those examples where we should just continue reading, huh?
I would think so.
Image channels. Ah, okay. So it's just a different
RGB or whatever.
Axis. But what's an axis? Like, so RGB are each a
Thus,
channel,
there is no deep sound channel in the ice-covered Arctic Ocean in the winter, since the minimum temperature. Something tells me it'd be more useful to keep reading. Also, it looks like our model finished training, or whatever. Oh no, it's not. It's still working.
You're just trolling me.
I should have looked at the little favicon at the corner. Anyway, so I guess
we already know what's gonna come out there.
Yeah,
look at it.
All right, as we expected, the mean and the standard deviation are not very close to the desired values.
Where do we see that? Is that giving us like mean standard deviation stuff here? What?
I don't know.
These outputs. Fortunately, normalizing the data is easy to do in fast.ai by adding the normalized transform. This acts on a whole mini batch at once, so you can add it to the batch transforms section of your data block. You need to pass this to the transform. Do you need to pass to this transform the mean and standard deviation that you want to use? Fast.ai comes with the standard ImageNet mean and standard deviation already defined. If you do not pass any statistics to the normalized transform, fast.ai will automatically calculate them from a single batch of your data. So add this transform using ImageNet stats as ImageNet A is a subset of ImageNet, and take a look at one batch now. Okay, we can't do any of that yet because we're still on this.
Amaze is doing 5?
Yeah, I think so. So it's gonna be a bit.
Yeah, probably another 10, 15 minutes. Okay.
Okay, anyways, we got the outputs already. Okay, so what are we doing? Conceptually, what we're doing is he's saying that we want the channels normalized, or the is that what it means? So okay, so we've got pixels, and they're on color values between 0 to 255 for each channel. So maybe we have an RGB image that has per pixel, it has 3 channels, and each of them has a value between 0 and 255. Right? Yes. Or we have CMYK, and then it's 4 channels, and each of them has a value from between 0 and 255 maybe. Or maybe 0 and 1, I don't know how these ones are. And we want to have a mean of 0 of what? Of all, a mean of what? Of all pixels across one image, or of all pixels across all images?
I don't know. You hiding? You look like a burglar. You know, like those the old like a villain from a superhero movie. It's like, who is that? Where did Martin go? With the mustache and everything. That's a good little laugh. Oh, there he is.
Oh, why? What do you mean? I just had to go for a second.
Oh, man.
So what? So we're not understanding this, or what? Is that what's happening?
I think that's what's...
Is that what's happening?
I think what's happening is that the motivation to learn something new is just dropped. We just...
I can't hear you anymore.
All right. Well, I can't even...
Mike?
I can't even scroll or do anything. You didn't really miss much. We read a bunch of stuff. We're training a model, and then Martin decided to be a supervillain, and he had a nice little laugh, a little mustache twirl, and now I can't control his screen. Oh, there he is. Now he's back. And now I don't know. I think he's gonna do it again. Oh no, he's on his exercise ball.
I'm on my bouncy ball now.
Yeah.
It's gonna keep my brain moving.
But yeah, no, Jonah Vision, I would definitely be confused if I left the computer and I came back and you see Martin looking through his mic like a villain. Okay.
You just got stuck. My brain got stuck, and
yeah.
I think I infected Nick.
Can you click on this link by that Mellinger said? Mellinger posted?
Okay. Or I can't really, because I have this.
I'll paste it in the chat. Hold on, give me a sec. In the Zoom chat. There you go.
What is the chat? Okay, we got something. And I'm opening it twice, just to be safe. Why are mean 0 and standard deviation 1 distributions always used? My stats has been soft out by a lot of material. I read points that data set having mean. What does it even mean for a data set of images to have a mean of 0 and a standard deviation of 1? Okay, maybe this is also explained here. Wise means 0 and ST1 a nice property to have. 0 the chance of drawing 0. Okay.
Yeah,
I think the most useful answer.
Now I'll let you go finish this. No, I was gonna say, I think we've covered this in one of the earlier chapters of the course, but the question was more related to like the images and the pixels and the values and like these different channels that we're kind of not really understanding. So it's like the mean of what, right? That's the question.
Yeah.
Not so much like why is the mean 0, but like what are we taking the mean of to equal 0?
Right. Is it like the pixel, like is it the 0 to 25 pixel values across all channels of one image? Or what does, I'm confused. I guess I don't understand stats enough for that to make intuitive sense.
Yeah, my question, right, like what I'm unsure of is like, what is it taking? Like it says image, like your input data is normalized, but what part of the input data is normalized, right?
It must be the pixel values. That's the data that we have, right?
Like the RGB values of each pixel. It would make sense, right? 0 to 255 as RGB values, no?
I mean, that's one band of the RGB, like that's R.
Right, R, G, and B, right? But the values are between 0 and 255.
And then it normalizes that to what? Be the mean of...
Okay, so John Vision saying, it's the mean of the pixel values. Yeah, for each color. Okay. And we want the mean to be 0.
So the mean across all images in the data set is what we want to be 0, so that any, like, that would be the mean. So the red, that is the average red across all images, is going to be 0. And then whatever each image deviates from the average red across all images is going to be a certain number above or below 0. So I guess that's how I understand it. And that's for each color then.
Yeah, John Vision just confirmed what you just told me.
Okay, nice. What's the average? 128. I guess that depends on the data set. What's going to be the average value for red or green or blue? Red, green, blue. Right? Depends on which images are part of the data set.
Yeah. Something also tells me, like, if we continue reading, we're not going to get the answer on this one for some reason.
You think so?
I don't know. Maybe.
Well, this makes sense to me now. Like, I can understand that somewhat.
Okay.
All right.
Go ahead.
And so what are we getting? So and this one here, okay, x dot mean dimension 0, 2, 3. So we're looking at one batch, and then we're getting the standard deviation of, okay, so these are the images. These are all the pixel, like all the images of one batch. The data, the actual image data is x, and then we're getting the mean of it and printing that out, and then also getting the standard deviation of it and printing it out. So this here is going to be the mean.
Yep.
0, 2, 3. I'm not sure about that. What's that? 0, 2, 3? Dimensions.
Yeah.
It's taking the mean over specific dimensions of the images. Yes.
Yes.
What do you think about just saying yes to that?
Yes.
Yes. Okay. Great. So here's our average, our mean, and that should be 0. That we would want that to be 0, but it's these 3 numbers instead, and we would want this to be 1, but it's these 3 other numbers instead.
Yep.
Cool. Deal.
Cool.
Buy it.
As we expected, the mean and the standard deviation are not very close to the desired values. Fortunately, normalizing data. Okay, we said this already. This acts as a whole mini batch at once. Doing the batch transform section of your data block, you need to pass this transform to mean standard deviation that you want to use. fast.ai comes with the standard image net mean and standard deviation already defined. If you not pass any statistics to normalize, okay, we read this already. Yep. And then we're just waiting for the model to finish.
But
so we can
now we understand
running.
a little more what this is about.
Yeah.
Okay, so and now we're doing this. Now we're passing the normalized from stats. So we're passing the normalized to the batch transforms. We can do that. And we're taking the statistics from the ImageNet because they're included in fast.ai already. So there's not much we have to do. Fine.
Yep.
Then we're getting
the data loaders.
Is that one batch?
XY.
Do you remember what these numbers are? Is I know 64 is one batch. Is the batch size that we used, and 224 is probably like the image size that we defined somewhere.
Isn't it right there? We just defined that function get DLS.
225. There it is. Image size. Size of the transform. Ah, yeah, you're right.
Right there. Get DLS, and then we're just passing 64 and 224 into it. Cool.
Yeah. I see. Okay. So we're defining this function. Okay. Okay, I see. Yeah. Interesting why they're doing it like that.
Yeah.
Okay, and now
let's keep us on our toes.
This. So this is closer to 1 than it was before.
Yep, and that's the top ones.
I don't know if that's closer to 0 than it was.
Yeah, it is. The last one's not really that much closer. I mean,
0.4, 0.4. 0.07. Okay, it's way closer. Yeah. Yeah, the last one. I see what you're saying. Okay, it's better.
And then we check if it's got, and then we have to train again. Okay.
Fit one cycle. That's gonna take forever, huh? Well, does it in a minute.
Yeah, but this is like Jeremy's showing off or something. They have priority access to collab or something. Ours takes usually twice as long. Why does ours take 3 minutes on this?
Change runtime to prioritize GPU. Although it only helped a little here, normalization becomes especially important when using pre-trained models. The pre-trained model only knows how to work with data of the type that it has seen before. If the average pixel value was 0 in the data it was trained with, but your data has 0 as the minimum possible value of a pixel, then the model is going to be seeing something very, very different to what it is intended to. This means that when you distribute a model, you need to also distribute the statistics used for normalization, since anyone using it for inference or transfer learning will need to use the same statistics. By the same token, if you're using a model that someone else has trained, make sure you find out what normalization statistics they used and match them. Makes sense? We didn't have to handle normalization in previous chapters because when using a pre-trained model through CNN Learner, the fast.ai library automatically adds the proper normalized transform.
It's finished training, just so that we get the other one starting to train it. We can compare the two.
Okay, so what we got 0.83 and then
just run everything under that.
And it's gonna get better. 0.83 and we're getting it to 0. less.
Well, hopefully,
we'll see.
Hopefully
it's gonna be better.
Yeah. Cool.
Maybe this is faster. We'll see. We didn't have to handle normalization in previous chapters because when using a pre-trained model through CNN Learner, the fast.ai library automatically adds the proper normalized transform. Okay. The model has been pre-trained with certain statistics in Normalize, usually coming from the ImageNet dataset, so the library can fill those in for you. Note that this only applies with pre-trained models, which is why we need to add this information manually here when training from scratch. All our training up until now has been done at size 2 to 4. We could have begun training at a smaller size before going to that. This is called progressive resizing, or PR.
All right, progressive resizing. When fast.ai and its team of students won the Dawn Bench competition in 2018, one of the most... Why are you shaking your head?
They're just rocking everything. ImageNet, building something, winning something, posting about it.
Right.
Making a good course.
That Kaggle German team needs to step their game up. Maybe they need to take some notes about actually winning
Berlin
some
team.
stuff. The Berlin team, right? One of the most important innovations was something very simple. Start training using small images and end training using large images. Spending most of the epochs training with small images helps training complete much faster. Completing training using large images makes the final accuracy much higher. We call this approach progressive resizing. Jargon: progressive resizing, gradually use larger and larger images as you train. Cool. As we've seen, the kinds of features that are learned by convolutional neural networks are not in any way specific to the size of the image. Early layers find things like edges and gradients, and later layers may find things like noses and sunsets. So when we change the image size in the middle of training, it doesn't mean that we have to find totally different parameters of our model. Okay? But clearly there are some differences between small images and big ones. So we shouldn't expect our model to continue working exactly as well, with no changes at all. Does this remind you of something, Martin? It's okay if you say no, because that's my answer.
No.
Okay, me neither. When we developed this idea, it reminded us of transfer learning. Okay, I get it. Sort of. We're trying to get our model to learn to do something a little bit different from what it had learned to do before. Therefore, we should be able to use the fine-tune method after we resize our images. There's an additional benefit to progressive resizing. It is another form of data augmentation. Therefore, you should
got it a bit later.
Therefore, you should expect to see better generalization of our models that are trained with progressive resizing. To implement progressive resizing, it is most convenient if you first create a getDLS function, which takes an image size and a batch size, as we did in the section before, and returns your data loaders. Okay, that's why they did that.
That's why they did that.
Yep. Now you can create your data loaders with a small size and use fit one cycle in the usual way, training for a few less epochs than you might otherwise do. Okay, so we have DLS, get DLS, and then we're passing. Okay, interesting. So
they're taking they're increasing the batch size and reducing the image size for the transform.
Right.
And training one less fit one cycle using the same. I guess the rest seems to be the same.
Yeah. Was it also on XResNet 50 on the previous one? I think so.
Yeah.
Okay. How's the previous one doing? Or we should be like in the third epoch now, at least.
Should we?
We should be.
You think we should, huh?
I thought we should have been.
Well, we're not. You could play some guitar in the meantime if you wanted to.
I have to tune that guitar. If you really want to hear me tune a guitar, I think we have some other stuff that we could be learning.
When you tune your guitar, do you do it with a tuning device or do you use your ears and the vibrations?
I'll do one string. So I'll do like the top E string with a tuning device, and then the rest of them I do by ear.
Do you listen for the sounds, or do you listen for the vibration difference of the waves? I guess
both.
you do the sounds if you don't know what I'm talking about.
No. It's both.
Generation says it's a prop. Looks like it. I've never heard Nick play the guitar. Just say I've known him for a couple of years and I've never heard him play the guitar. Just saying. I personally also haven't played the guitar for a couple of years, so it's understandable. But I don't have mine standing behind me so that everyone knows what a cool dude I am.
Today's a day that the cool.
Visualize them.
Today's a day that it backfired. That I actually had to pick up the prop. Thanks, Jonah Vision. Used to just be a cool prop.
So what? Hit it. Well, yeah. I'm just gonna fill the silence, saying that I'm never able to hear the sound, the different tones, like to put them the same tone, but I'm able to hear like when the waves are different, like when they're different tones, then they kind of go like wah, 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 wah.
Yeah, so that's how
when they're the same, then they stop. Then they stop doing this.
Yeah,
that's what I can hear.
All right.
So are you gonna play?
I'm gonna play a tuning. That's
tuning tune. Play a tuning tune. Ooh.
Maybe that's what you hear, no? Hold on.
What?
I don't know if this is...
So you tune with the upper octaves?
What?
You tune with using the upper octaves?
I start with the E, the lowest string, the E string, the top E string, and then I just do they're called pitch harmonics. So if you have your
right,
which I think is what you were saying with the waveforms, so it works. Huh? Anyway,
I didn't mean those. I didn't mean the pitch harmonics.
Yeah, so I just use pitch harmonics up until like the B string, and then you have to tune that one with like sound again, not using this like vibration. I think the pitch harmonics is what you were saying is vibration. I don't know what.
No, I just do the like.
What do you put like your barefoot
fret?
You put your barefoot on the guitar, and you're like, yes, this is a G. This is a D.
Yeah, that's how I feel vibrations. Isn't that what you do?
No.
I have no idea about tuning guitars, huh? We're nearly on the third epoch. You know, there's this fun meme. I'm gonna look at this. Waiting. I think it's XKCD comic. I'm not sure though. No, it's not XKCD. Model Rails. Code compile.
Can I play Smelly Cat? What is... I don't know what Smelly Cat from Friends is. Let's see.
Yeah, that's the one.
What is it? I've seen the show Friends. Like, I'm not even gonna say I've seen the show. Like, I've seen a couple episodes. I can't say that I've seen every single one. But I don't know the song Smelly Cat, but I can find it and play it. Let's see.
I think that's a cute meme comic. I think model training is like the modern equivalent of code compiling. I'm gonna shut up now. Who cares? No one cares.
Can you find on like YouTube or something Smelly Cat?
Me?
Yeah.
But it's not gonna play if I play anything.
But it all, you say that all the time, and then it like does very quietly. Yeah.
Okay. YouTube Smelly Cat Friends. Oh. YouTube privacy warning.
We flagged that video.
It's an evil video. Do not watch. I also don't know this song. I shall be honest. Okay, I think so. Do you hear anything?
No.
You don't, huh?
Maybe if you share your screen. Oh, I sort of hear it. Well, you should take one of your headphones off and put it next to the mic.
Wait, I'm confused. This is too much work. Is that the song?
General Vision saying that's not it.
I'm not.
Seems like it would be it. Smelly cat.
It does seem like this would be very easy to play on the guitar.
I have the chords in front of me. I just don't know what it would sound like. So.
Well, can't you read the chords and know?
I can, but it doesn't say like any.
Oh, so that's what I like.
Oh, maybe the first one, or that one.
Maybe that one. All Friends.
The Smelly Cat jingle. Hit the third. I don't know.
I'm gonna start off with a little.
Oh, there we go.
Should I do this one?
Yeah.
Okay. Little song called Smelly Cat. For those of you who are wondering, this is my real voice. Smelly cat, what are they feeding you?
Okay.
Everybody! Smelly cat, it's such a ball. Monica, won't take you to the bed. Taylor! Joey!
Okay.
Do you think you can do it?
I think so. Do you want to pull up? Do you want to sing and then I'll play?
No.
I think it's just smelly cat. What? I don't know. What are they feeding you?
What are the chords? Is it like
E A D A?
Oh, okay. Yeah, because you can do that.
Thank you, everybody. My world debut of Smelly Cat. For Jonah Vision. Taking more requests. Fast AI. Why does it take so long to train?
That's great.
Thank you.
I've just first time seeing you play the guitar.
That's not, really? What a treat.
Think so. When
what
else
a treat.
would I have?
Smelly Cat is your first experience.
It's my first Nick song. Impressive. Yeah, we're also. Yeah, I think it's on its last. It's on its last leg.
I keep forgetting that we have music playing in the background because I don't hear it. Like in the back of the stream.
Oh yeah, you're right.
Yeah.
Mm-hmm. True.
Well,
do you think you were in tune with the chill music? Okay, so we got up to 0.8. It's actually got worse. What? 0.82, and it used to be 0.83. So this got worse. Why is that?
Although it only helped a little here.
It just helped to get worse.
Well, hold on. It says, although it helped a little here, I guess start this one. It says the normalization helps something else.
Okay, wait, let me go. Scroll back.
Yep, right there. Normalization becomes especially important when using pre-trained models. The pre-trained model only knows how to work with data and the type. So I think, maybe it got worse, but they're kind of explaining, I think, a little bit later on, a little bit further down is how it's going to get better, no? Or this, like...
Just says...
progressive type of learning, progressive resizing.
Okay, sure.
What I'm saying is I don't think they always have to get better. Like those numbers.
I have this song in my head now. I can't think.
Thank you, Jonah Vision. Smelly cat. Start thinking about, songs for our intro and outro. Maybe not at the tune of Smelly Cat, maybe something a little bit different. Or maybe that, because it's very, catchy, apparently.
It seems to be.
Nick and Martin learn some stuff. Sometimes. That's all I got.
Sometimes. I think it's like very descriptive. So
That's it. That's the song. Nick and Martin
So why
learn some
not?
stuff. Sometimes. Thank you, everybody. That was our intro song. All right, so what's happening after this? Let's keep going because we were gonna.
This is supposedly going to be much faster now. And then replace data loaders inside the learner, and we do another. This is a lot of training going on here. Then you can replace the data loaders inside the learner and find you learn the DLS. Okay, it's replacing it.
Training for another 5 epochs. It's also changing the
so we're first
that like learning rate or
no, it's just changing the data loader that you're using.
Yeah, but also like fine tune that second parameter. This one's 1.
You're right. Yeah, you're right. Okay. It's doing an additional cycle.
No. That 4 versus 5, but also the second parameter 1e minus 3 versus 3e minus 3.
You're right. Everything's changed. It just makes the resemblance of being similar, but in fact. So, do you understand anyone out there in the void? Do you understand why they're using different batch size here? And then they're like, I get this progressive image resizing. We're doing 128. We're snipping them in half. Not really in half, I guess. We're making a smaller one. And then, but why are we also changing the batch size? Because now it's going back to 64 to 4.
I think it's just I think for this it's just for the sake of time. Like it's using a smaller batch size because we're using larger images. So training wise is going to be faster. That's my guess.
Okay.
And also maybe it doesn't need, it was saying as the images get larger, it's getting better and better. So we don't need as large of a data set, right? Kind of like why ResNet exists is because it's pre-trained on, and then we're adding, I think it was saying in the beginning, it's one of the questions in the questionnaire was like, what are the things that we don't need to do machine learning? And one of them was a large data set, right? Also, like 64 images versus 100 images is not really a huge difference. That's why I think it's just for the sake of time.
But that's just the batches. That's just the size of one batch.
Right.
Okay.
That's what I'm saying. I think they're trying to just show that it's getting better as like we're progressively getting larger, and just so that we're not spending so much time training, they just reduce the number just to prove the point that the accuracy is getting better. My guess. Who knows?
Feels a little unscientific to me if there is not a reason, a specific, if it's just like we just changed this and we don't even talk about it.
Well, they also changed that second parameter and they're not talking about it either.
Maybe they are. As you can see, we're getting much better performance, and the initial training on small images was much faster on each epoch. You can repeat the process of increasing size and training more epochs as many times as you like for as big an image as you wish. But of course, you will not get any benefit by using an image size larger than the size of the image on disk. Note that for transfer learning, progressive resizing may actually hurt performance. This is most likely to happen if your pre-trained model was quite similar to your transfer learning task and dataset and was trained on similar sized images, so the weights don't need to be changed much. In that case, training on small images may damage the pre-trained weights. On the other hand, if the transfer learning task is going to use images that are of different sizes, shapes, or styles than those used in the pre-training task, progressive resizing will probably help. As always, the answer to will it help is try it. Another thing we could try is applying data augmentation to the validation set. Up until now, we have only applied it on the training set. The validation set always gets the same images. But maybe we could try to make predictions for a few augmented versions for the validation set and average them. We'll consider this approach next.
Test time augmentation.
Augmentation. There it is.
There it is. Yep, I think Jonah Vision's right. You're going to be falling asleep to this later.
right.
Crazy that 20-second video of that song is going to be stuck in your head now for the rest of the day. It's so catchy.
That's the horrible thing with like simple, progressions of chords. They're just very, very toxic.
Maybe one of these streams will do Nick and Martin learn how to produce music.
Oof. Also a long-term idea of something I would want to do, but never do.
Or we can learn how to be DJs. And we can do live sets on Twitch.
Smelly cat.
Smelly cat, smelly cat. I think we could do really well. There you go. Nick and Martin become famous DJs.
Yeah, I feel. Anyways, Nick, I don't really want to do this test time augmentation anymore today. How do you feel about this?
I mean, now we're getting to look, some like harder math stuff.
There's even hidden cells.
Papers
I didn't know
and
about
math.
that.
Look, there's some Greek letters in there.
You feel at home.
Wow, some gas stations.
Ooh, there's images.
Wow.
Yeah, but this is more than my attention span is happy with for today.
Totally. I thought we should have skipped this whole thing altogether.
Right, you said that.
No, that's fine. We could pick this up on Thursday.
Wait, so what did we learn today?
Recap. Okay, so progressive resizing. I think we learned that today. We haven't really proved it yet.
No, but so the concept that you can increase, if you have, if you have different images that, like you have a data set that you're using, and then the images that you're actually working with, like your data set, no. So you have a model, you're using a model, but it's been trained on a specific type of images, and the data set that you're using actually has pretty different type of images in terms of size or whatever. And if they're pretty different, why don't you do a sum up?
I think just the concept of training. So what you were trying to sum up, I don't really fully understand yet. And I was kind of hoping we'll just review that on Thursday, and I'll probably get it then, because it's one of the last things that we said. And like my brain is also kind of turning off at this point. But just the concept of training or your initial model on smaller images and then progressively getting larger has a positive effect on the training or the predictability later on, because
but I think
it's also speed.
But only if the data set that you're wanting to predict on, like your data set that you're using for training, is different from the data set that was used to build the model. I think that's like an essential factor in it, because they also said later on that if your data set is actually similar to the one that was used to train the model, then doing this progressive resizing can.
That's the part that my brain shut off on.
Okay.
Yeah.
So
but that's a good point. Okay,
yeah.
Cool. Yeah, and then something about sunsets and noses and a very other.
Another thing, like the normalization, like you want to have your mean at 0 and you want to have your standard deviation at 1. And what that means in terms of images is something I kind of understood, is that you want to just find the average value for each of the channels and then normalize with some built-in methods that they already have, so that all the values of all the images in your data set kind of like hover around that mean, at the mean of 0.
And what else? We learned some cool like printing things for scientific notation.
Yeah. Scientific notation. Yeah.
We learned some cool printing things.
So look, this is 7.7587E01.
Minus 01.
Yeah. Okay. You're right.
And what else did we learn? We learned the annotate. I've never used annotate on Zoom before. That was exciting.
Nice.
And finally tuned my guitar the last 3 months. It's been sitting there untuned. I learned how to play Smelly Cat.
What was it? What's the chord? The chords?
E-A-D-A.
E-A-D-A. Cool.
E-A-D-A.
I learned how to play too.
E-A-D-A. There you go. And now you learned a new song that's going to be stuck in your head forever. Good luck.
Okay.
Okay, that's a good tip. If that helps you, Martin, scientific notation, you say times 10 to the negative 1.
What?
I don't know.
Why do they keep getting worse?
Oh, wow.
It's
I think it hurt us play Smelly Cat. It's also distracted.
Every single one, like it's from the first one, it's just been getting worse. Look at that.
That's what I'm saying. Let's just keep the magic of fast AI the way it is. Why do we have to learn all this under the hood stuff? This is just optimism. And
this is just this is dumb. This is just a small one. Like that's just step 1 of progressive resizing.
Isn't this also like, you know, in the beginning, the first paragraph was like, this is optional.
Oh wait, what are you saying? The loss function is decreasing? Is it 0.7? 0.7? No, it's going up. The loss is going up.
Were those on the same one?
0.5. What?
These are all for get data frames? Get DFS? No, this is totally different.
No, that's the first one that we ran without anything.
Right.
And that the loss is 0.54 and the accuracy is 0.83. Then we did the normalization, ran it again. We have a slightly higher loss.
That's the first one now.
And a slightly lower accuracy.
No, isn't this the first one? Because we're defining this new like DLS. Right? Scroll up a little bit more.
I don't know what you're asking, but
right?
I should scroll.
Here. DLS, we're defining a new data loaders, right? We're defining this new data loaders called DLS over there, and then we're doing the DLS1 batch further down, or like the fine tune or something over here. No. Okay, learn.fit. We're using DLS. So this is the first one. Well,
that's the first one after we normalize. Before we ran one training without normalization. Gotcha. Yeah. And what are you saying? Mellinger says in each epoch it goes down. Yes, per training, like the loss goes down and the accuracy increases. That's what we'd expect. But in comparison to the previous trainings, like here it goes down and it goes up here. But comparing the last epoch to each other, it seems that the normalized one actually does worse than the not normalized one. And then
but there was a whole paragraph on that, on like why it may be like a little bit better. So I'm thinking it could be a little bit better, it could be a little bit worse. Like it doesn't always have to be. If it's so close, I feel like it can go either way. And then the results of these may show something else. I don't know.
Yeah, I mean, this one starts off much better now. Look, this starts at 0.7 for the loss and 0.7 for the accuracy.
Right. But now here, so
as compared to these ones, these are much worse. Like this has a much higher loss and a much lower accuracy for the first epoch.
Maybe I'm getting confused now. Hold on. Can I just remote
just
control?
Because I keep scrolling so much?
Yeah. So
it's really good.
So here we have, okay, so we're defining this new one, S, here.
Right.
And we're building it off of.
Have a nice day.
All right, yeah. see you later, Genovision.
Or epochs doesn't sound like many. Yeah, but actually, I don't know. Have you said you haven't done the course yet, right? So the fast AI is actually designed like in a way that you often don't have to run more than these 4 epochs to get pretty good results, because it's building on top of a bunch of abstractions and things that were already like. I think it often uses transfer laning. I'm not sure whether this one does use transfer laning though. Kaggle, yeah. Does Kaggle, on the Kaggle ones did you use any fast AI? Or 50, yeah. I think those those Kaggle exercises, they're often not working with fast AI, but they're just using like direct, like building their own models and then training on top of that stuff. But here, a lot of the things that you do is you use a pre-trained model and you use some transfer learning, and then a lot of you get pretty good accuracies with just a couple of epochs. It's actually quite cool. Yeah, you should check out the course, especially if you have already some experience with machine learning stuff. It's going to be interesting. But in that case, like I was just thinking about comparing the different, like we've been running the same amount of epochs for each of those and just changing small parts. Like for one time we're doing the normalization. For the first time we didn't do the normalization, and then now we're doing 2 steps with the progressive resizing. And I'd expect it to get better because it's the whole point of this, but it seems that it isn't. And I'm not scrolling at the moment, I'm just saying. Also, other people scroll a lot.
So this is the first one that we're doing here. And we started with 4, 5, and we ended with 8, 2. And then we're now down here, we're doing progressive resizing. And we're doing it for one less cycle. We're starting around, okay, this is 4, 4 versus 4, 5, whatever. And then sending at 7, 8. So, because here, that was my point, is like, we're overriding this learn variable. Like, we're creating a new learner over here. And now we're doing the 64, 24 down here, just building on top of that. Step 2, right? Correct. So the first one up here, it's just step 1.
That's the second one. So there's three times that we're training, even though there's 4 times training.
I know, but so this DLS 64 to 24, we're using that DLS over here to define this learn, and we're learning for 5 epochs. So that's what I'm saying. I don't think we can compare this result that uses fewer images at higher resolution to the one down here where we're just starting that uses more images with lower resolution. So I don't. But we can't. That's what I'm saying. I don't
compare it with the first one.
Okay, so let me see. So the first one.
Yeah, we're still waiting for the third result essentially because it's on step 2 of the 2 steps.
So this one, you're saying
that resizes to 224.
Okay.
And uses 5 epochs. 224. But it doesn't do the normalization. That's the difference.
Right. I don't know, maybe it just sounded like the comparison sounded weird. Like it felt like we shouldn't be comparing those 2 things because they were very different. But
no, I agree.
Maybe, okay, never mind then. Stopping remote control.
Yeah.
All right, cool. So what are we gonna do? We're just letting this.
Let's wait for this to finish.
How many more cells? So what's after this?
That's it.
Test time augmentation.
Like we're not gonna go over test time augmentation.
Okay. So let's see what this one looks like.
We're waiting for this 2 more epochs.
Yeah, 6 more minutes.
I guess. Yeah, 6 minutes. Just to get a result and then actually compare. I guess I can copy this to do something in the meantime. I can copy these different results so we have them in one place. So this one is going to be with normalization, but not progressive resizing. Oops, I keep pressing the wrong button here. Okay. Normalization, and then we have one just default. first one. Default, normalization, 4, and then we have one more. That is normalization and normalization, progressive resizing. Is that right? Did we do normalization in this one too? We're using learner, data loader, cross entropy, get DLS. Yeah, get DLS. We're using that one too, so it does the normalization.
Mm-hmm.
Okay. Keras, what's that? So I know fast.ai is built on top of PyTorch, which itself, no, that's a library, right? Like PyTorch, you've got TensorFlow and PyTorch are the big two machine learning libraries in Python. I think Keras is built on TensorFlow.
Yeah.
I think so too, yeah. Let's see. TensorFlow.keras.
Yeah, it says right there. Small compact library built on top of TensorFlow.
In the first for the TensorFlow library.
So who built, so TensorFlow is by Google, right? PyTorch is by who? Facebook?
I think maybe.
Yeah.
Facebook AI Research Lab.
Yeah, that was like a thing. Were you saying it one of the previous streams or somebody else maybe? Where Elon Musk was going off on Facebook, on Twitter, and then the SpaceX and Tesla employees were like, yeah, but we could still use PyTorch, right? And Elon was like, yeah, that's still fine.
He was complaining about Facebook or what?
I think so. Maybe Jonah Vision was saying that in one of the previous streams, yeah.
Is fast.ai in here? No. Fast.ai. Just checking, but I think it's on PyTorch. PyTorch, yeah. Sitting atop PyTorch. Yeah, so I guess fast.ai is similar to Keras, just built on top of a different, like as a higher level library, but just built on top of different machine learning library. 49 seconds.
But then I think there's one more, right? Or no?
No, the fourth one should be the last one. I mean, yeah, it does this second pass, whatever that second pass is doing. You know, like it does this one bar and then it does a faster second bar. But 4 is the last one because it's got just five epochs, I think. Yeah, we just got 5. And yeah, you said like the learning rate is different, right? So I guess, no, this is anyways different. So 1e minus 3.
The other ones were 3 minus 3.
3e. Here they're using 3e in the first step, but then they're using 1. I wonder why. Magic of the numbers. So you like my my new image?
I like it.
Can't think of a name. Okay, there we go. Okay, it's going up a little. All right, let's pop it in there. Compare this. call it a day. Okay, so here we go. Default, the one we started off with without normalization, 4 epochs. What was that? So this is the loss. I forgot what the first one is. And the third one is accuracy. They take the same amount of time. Didn't he say that it makes them faster? No, it just makes, these ones are also not really faster.
Yeah.
With the smaller images.
Yeah. The previous, like with the example, it was all the same thing. It was like 1 minute, 14 seconds throughout around on all the epochs. So.
Okay, but we get, so the first time, just with normalization, we get a drop in accuracy and an increase in loss. But then if we do this progressive resizing, both compared to just normalization, but even just the default one.
Right, significant reduction in loss, but also pretty significant increase in accuracy.
Yeah. Okay. Training
loss, validation, and accuracy. Yep.
Yeah. So Melling is saying that if you increase the epochs, you can do that. So in fast.ai, you can just drop in like this is the number of epochs that it's going to run. There's also different methods that you can call. Like there's fine tune, which is one of the ones that performs training, and this is the amount of epochs that it trains. You see, like it does. I'm not sure what the first one is here, but then it does 5 epochs.
The first one was a default frozen one.
Is that in fine tune?
Yeah,
it's like that?
In fine tune it freezes 1 by default.
Okay, so it does this training on the frozen on the model, like the model that you're passing into the data loader, or is it XResNet 50 in that case? So it keeps all the parameters as they are in there. It doesn't change anything, and trains just like with the default parameters from them, plus has like a couple of layers, like I think 2 layers. Of your data. That's the first round, and then it unfreezes the original ResNet or whatever model you pass in, and opens up all of the parameters to change, and then it trains for 5 epochs essentially. This is what it does. And if you want to run it for more epochs, you can just change this number here. So if I do 10 here, then it would run for 10 epochs. Or just continue doing them for 3 minutes each, and it might go a bit better if you train it more, but you see the increase between the last 3 isn't actually that big. So the way that this library is built for some reason is that like usually you get to that, that result that caps it off in terms of increase in accuracy already around that amount of epochs. But yeah, and you could give it a try. Like I'm gonna pop this over to our GitHub.
Yeah, the other thing too is I noticed that you also, guessing it was you who just subscribed to or followed us on Twitch and on YouTube. So thanks for that. But on YouTube, we posted all of these like non-edited live streams that we've done in the past. They're all like super long, but we did our best to kind of categorize them and timestamp them in the description. So we do talk about some of this stuff and the different types of like training in those other streams. But I think, and if you want, you can go ahead and like look at those, but definitely look at the descriptions, because some of them we do go off tangents quite a bit.
As you've probably seen.
I
make a copy.
I think the best is probably just go through the course, fast.ai, like go through their notebooks and kind of, since you've already have experience with like Keras and Kaggle, then you got some understanding of how to use the libraries, and it may make more sense because we're coming at this with no real previous experience, right, Martin? I'm speaking for myself, of using any sort of AI or machine learning libraries.
I've read a little bit about it. I've played a tiny bit with it, but not really anything. Why can't I not make a copy? Usually I can make a copy.
It's like duplicate notebook or something.
Do you see it anywhere? Save copy in Drive. I mean, I'm just gonna save a copy in Drive and then I can push it from there. Because
I think that's how we do it. That's how we've been duplicating it. Yeah.
Okay.
Because we've just been keeping it in Drive, and then.
Maybe you can only duplicate it when it's in your own Drive already, something like that.
No, what I'm saying is I think this is how we've been duplicating it. is just making a copy in Drive.
Cool. All right, I'm gonna push it to GitHub. Proportional resizing. Cool. So if you want a Mellinger, maybe you want to run the notebook yourself and see if like run it with a couple more epochs and see whether it would be interesting if it actually increases. I'd like to see that, because I don't think it's gonna. I understand the intuition though that you should run more epochs and then it would go better, but like from what I've seen so far with fast.ai, this is not, it's just like built in a pretty good way that it reaches the cap off point pretty soon. But yeah, go ahead, check it out. We have it linked, the GitHub, and try running it. Maybe if you run it for 10 epochs, it actually gets better. It would be interesting.
Mm-hmm. Cool. All right. So we'll pick this up on Thursday.
Yes, we do part 2, right? We're gonna go over test time augmentation.
Sounds good.
Woohoo!
We did it.
Nick played the guitar.
We did it. We went back in and we started learning again.
True. Yeah, we continued a little bit on the chorus. That's actually something.
Yeah.
Time is gonna be always the same. You check on our Twitch also.
Yeah, 11 a.m.
Same time
Eastern.
as today.
Yeah.
11 a.m. Eastern. We have I think the thing is a little outdated because it still says that we're building on Monday and learning on. Maybe we get back into that. We'll see.
I don't think.
But the times are still the same.
Yeah.
This is gonna just be confusing. I'm not gonna do that now. But it's just gonna get weird.
Yeah, 11 a.m. Eastern on Mondays and Thursdays.
All right.
Cool.
Thanks for tuning in.
See everybody on
next time.
Thursday. Yeah, thanks everyone. Bye.